Hello everyone. In this video I'll be going through sections 8.2 and 8.4. So 8.2 is regarding creating scatter plots out of data. And just as an introductory example, we have these different years. This is a table of data right here. And on the right we have population of the state of Arizona. So this is meant to be 5,165,993 people, right, in the year 2000 and so on. And we're just tasked to create a scatter plot, basically making a visual representation of these numerical values here. So often it's hard to see patterns when numbers are just presented here in a text form. So what I've done here is created a scatter plot, and I've placed the population on the vertical, and I've just went ahead and said 6.5, 6.0, 5.5, and 5. So I've kind of started up here near 5, and then I've said population in millions. That way I don't have to write out all those zeros. On the horizontal, I've labeled it as years after 2000. And I've done that just again since I am wanting to avoid writing out all these thousands. I made this choice. So 0 years after 2000 would be 2000. 1 year after 2000 would be 2001, and so on. And this is the different data. So at 0 years after 2000, in other words, in the year 2000, we're at about 5.16. And that's what I had kind of estimated that first value to be. Anyways, that's what a scatter plot looks like. Moving on. So let's say we already have a scatter plot in front of us. So this is the total Wimbledon prize money. That's just a tennis tournament in England, and they just play tennis and then they distribute money based on the players, how they end up. The winner gets the largest chunk of this money, but the total prize money is plotted here on the vertical. And this is in millions of British pounds. So also this author of this graph decided, you know what, I'm not going to write out millions. I'm just going to say 0, 4, 8, 12, 16, and then just write over here that it's actually in millions of British pounds. Here's years since 2000 actually. So this would be 2000, 2001, similar to the previous one. And then it asks us to use this model, and the model is this line. So this line is the model. So it says estimate the total prize money in 2002. So 2002, I would look over here. So for this one, I would look right there, and then I would follow that over to the prize money. So I would say maybe about 8.1 million British pounds. So 8.1 million. That's my estimate. Part 2 says estimate in what year the total prize money at Wimbledon was about 9 million British pounds. So here's 8, here's 10, 12. So 9 would actually be right in the middle here. So I would go out from there, hit the line, and then track that down to what year for part 2. So in what year? So this is in the third year after 2000. So I'd say 2003. Estimate the vertical intercept and explain its meaning in regard to prize money at Wimbledon. So the vertical intercept would be right there. And I would say it's about so 0. And yeah, I'll say 7. So meaning in 2000, right, 0 years after 2000, the total prize money was 7 million British pounds. I'll just abbreviate it that way. What are a reasonable domain and range for this graphical model? So again, I'm going back to this line. And for the domain, that means the years in this case, the range of years, and just the numbers. So it looks like it ends here at 10. So the domain would be 0 to 10. And that would mean 2000 to 2010, by the way. The range is a similar idea, except you're now thinking not what X's or in what T's are included, but you're now thinking for what amount of prize money does it range to and from. So it looks like it'd be 7, right? It looks like the model goes from 7. And then up to, it looks like right here is about 13. So I'll say about 13. So about 7 million to 13 million British pounds. That's a 3. All right. Moving on to 8.4, we're talking about functions. Functions are an interesting part of this class, in my opinion. It's maybe one of the most important subjects in all of math, actually, are functions. And it doesn't matter whether you're in intermediate algebra or you're getting a PhD in math. It's likely that you're going to discuss functions quite a bit. So what are they? We're first going to need to talk about relations. We're going to learn about relations and then go on from there and talk about how functions are a special type of relation. So a relation is simply a set of ordered pairs. An ordered pair is nothing more than a first component and a second component. So this is an ordered pair, or triangle, circle is an ordered pair. It just has a first component and a second component, right? A pair. Here are some examples of ordered pairs: Shane green, Katie blue, Stephanie blue, Micah orange. Okay, just random examples. In this case, those ordered pairs are defined by this kind of general idea. The above examples are ordered pairs. They are ordered pairs of this type: the first name of a person, and then the favorite color of that person. And this is, these are people I know, but hopefully you can see the pattern there. These ordered pairs have some sort of relationship defined from the first component to the second component. Here's another totally different example of ordered pairs, or just a different set of ordered pairs. This first one says horses, 4, humans, 2, spiders, 8, snakes, 0, cats, 4. So what do you suppose is the general underlying relationship? So what is appearing in the first component, and then what is its relationship to the second component? So this is an animal. and then the number of legs that animal typically has. So within relations, we can group them. So we group them using these braces. I already had braces here, but when you group things with braces, it's said to be in a set. So this would be a set of ordered pairs, and that's what a relation is. Okay, when we have a relation, we can talk about its first components as differentiated from its second components. The first components, we call that the domain of the relation. The second components, the set of those second components, we call the range of the relation. So for that previous example, I have 4, 2, 8, 0. Notice that, oh, let me start with the domain, sorry. So here's the domain: horses, humans, spiders, snakes, cats. That is simply all these first components, right? Horses, humans, spiders, snakes, cats, grouped into its own set, right? This set here is the domain of this relation. Right, it's all these, the set of first components. The set of second components, I have 4, 2, 8, 0. Notice that I didn't write 4 again, even though there's another 4 for cats. So we don't repeat. So if there are repeats, we just state that entry once. Okay? So domain and range. Let's talk about the domain and range of these relations over here, and then we'll define what it means to be a function. So a function, so I've defined it over here, a function is a correspondence from a first set, called the domain, to a second set, called the range, such that each element of the domain corresponds to exactly one element of the range. So what that means is you can't have any repeats in the domain. So for these relations, are they functions? So we have chair 50, couch 150, TV 250, end table 40, coffee table 100. There are no repeats in the domain, so this would be a function. For the next one, here we have 1 going to 1, -2 going to 3, 3 going to 7, -2 going to 6. So here's a repeat in the domain, not a function. Again, just looking at the domain, no repeats, so this will be a function. Here, 2.5, -5, 1, -4, 10, we're in a situation where we have a repeat in the range, but that's okay. Nowhere in the definition of a function does it say that you can't meet at the same place. We just can't have one domain entry going more than one place. It's okay to meet at the same place. We're not allowed to go to 2 places at once. So there's no duplicate in the domain, so this must be a function. Let's do one more. So here's a set of ordered pairs. 1 goes to 2, 3 goes to 4, 5 goes to 6, and then 5 also goes to 7. So what you can sometimes do, if you need a little more clarity, is you can write the domain in a diagram, and then write the range in another set over here. And then I'll identify the correspondency. So 1 goes to 2, 3 goes to 4, 5 goes to 6, and 5 also goes to 7. So over here I wrote the domain, over here I wrote the range. This is the issue, right? We have a domain element going 2 places. That means we must have a repeat in that domain. So this is not a function because of that 5. So what we'll be doing largely is really working with what's called function notation. So this is where things get more algebraic. So what we've been doing is maybe a little bit more conceptual, but stuff that looks like this is going to be more what we're working with, right? These variables, operations amongst variables, and this is really what a function will be for us largely. But you can still think of this input-output scenario. So f, we'll see that these functions are sometimes called f. That's simply a name, just like you have a name and I have a name, just so we can refer to each other. Functions have names, and that's all that f is. You could have a function like g of x, and that function's name would be g. Maybe it's just x squared, but I would call that function g. That's all that is. This object is referring to the variable or the input. So you're going to replace, anytime you're looking for an output, you're going to make a replacement of the variable there. Sometimes you'll have, I don't know, h of t, and that would tell you have a function named h involving a variable t, and maybe it's just taking 2 times t, who knows. So that's the input there. Then f of x itself, this whole thing, is an output. So if I had like g of 2, I would square 2, I'd get 4. So g of 2 for this one, g of 2 would be 2 squared. In other words, 4 would be the output, and its name would be g of 2, and it would be 4. So f of x is the output given some input x. And then how do you get from inputs to outputs? You perform whatever algebraic rule is present. So this is a fairly complex rule. It says take whatever your input, multiply it by this result, and then multiply it by this result. Right? So this rule is kind of the machinery, the algebraic machinery that takes input to output. There's another concept here where you can kind of think of it like a machine, like a function machine. So you're taking on inputs x, like plugging in a 3. The function rule is taking effect, right? The gears are kind of turning inside of here, and then you're getting some output. So here's a function named f, its input is x, here's its rule, and we're being asked to find f of 2. So find f of 2. So f of 2, I take 3 times 2, and then I subtract 4. I get 6 minus 4 actually equals 2. So for the input 2, that actually goes to itself in this case. So domain and range, this is a picture of it. You kind of think of it that way. This is how it would represent a function. Just out of curiosity, what about f of 3? We're not being asked to do that, but we would find f of 3 by going 3 times 3 minus 4. So we would have 9 minus 4. This would go to 5. So in other words, 3 would go to 5. So each input, right, is going to go exactly to one output. So that's why this is a function. Here's another one. So here we have a function named g. Its input variable is x. Here's its rule. and we're being asked to find g of negative 3. So g of negative 3 would equal 4 times negative 3 squared plus 2. And then we perform this rule. I square first. Right, keep in mind I can always type this in here. So 4 times parentheses negative 3 squared plus 2. So 38. So if we were to kind of just draw a quick picture, we'd have that 3 for this one goes to 38 as far as domain and range go. That's how this represents a function. We're not being asked to find something else, but what if I wanted g of 0? We'd have 4 times 0 squared plus 2. So we'd have g of 0 equals 2. So in other words, 0 would go to 2. That's how this represents a function, because each input goes exactly to one output. Okay, graphing onto page 60. So graphing is simply a picture of solutions. So using the point plotting method, you can pick x's always, calculate the y's that result, do that a few times and you're graphing the equation, because you're finding solutions to that equation, and that's all an equation is a picture of solutions. So I can pick like negative 2, 0, and 2 maybe. I'm going to plug those in here. Those are going to be my inputs, in other words, and then I'm going to perform the rule and get my outputs. So 3 times negative 2 plus 2. So negative 6 plus 2, this is negative 4. So negative 2, negative 4. We have a point right here. Three times 0 plus 2, that equals 2. So we have a point right there. 3 times 2 plus 2, that is 8. So we have a point right there. So those are falling in this line here. So what we do is we draw the line through those points, and then we use arrows to represent that continues forever. So one way to tell that this is a function, by the way, is that it passes what's called the vertical line test. So if you imagine any vertical line, it'll hit exactly once. And that's what's going on down here, is we're talking about the vertical line test. So I would know right away that this is a function, this first one, because any vertical line I can imagine would just hit once. Same with this second one. But this one, you know, I can find several for which that's not the case. So that would mean that this one input goes to 3 different outputs, so that's definitely not a function. So that's the vertical line test. Domain and range, interval notation. So what we do for domain, we'll do this one in red, is we look at the inputs that are included. So looking at this one over here, we have inputs going from -2 up to and including 1. I'm saying and including because that's a difference that we need to make. So this includes, meaning the square brackets. So this includes the value because these are closed dots. These are including these actual values. We'll see over here in a second. This is meant to be an open. I'll just make that a little more obvious, but that's meant to be an open dot. We'll see how that changes things. But yeah, the domain is considering these values. What inputs were used to obtain outputs? The range would be those resulting outputs. So it looks like we went from here to here. So that would go from 0, including 0, up to and including 3. So this is part A there. So these all included because these all were closed. Right, these were solid points. Over here, the domain. So if you can see, this will be an open dot there, and then we'll include values all the way to 2 and including 2. So to exclude -3, I use a parentheses, and then I write -3 all the way up to 2, including 2. So I use a square bracket. So this excludes. For the range, this transfers over. We get an open right at 1. It looks like we have a closed right at 2. So 1, we're counting vertically now on the y-axis. 1, 2, and then closed at 2. For part C, so the domain, again, all these points transfer down. This is going to be open, this is going to be solid, and this will be the domain. So from -2 up to, but not including 1. So that's a parentheses there. The range, so we'll go from here, that's including up. This is initially open because this comes over, but then it gets closed. And then it goes all the way up here, and then it closes. So we'll have from 1 to 5, including 5. On to D. So here we have a closed point, and then we have this arrow. So for the domain, well, we'll need to imply that everything to the left of 4 is included. So what we do is we imply infinity. So we also have negative infinity going this direction, that way. And then all the way up to and including 4. Right, we would have this sort of line just on the x-axis. For the range, this will transfer over, it'll be closed, and then this also does go forever up. So we'll go from 0, 0 is the largest value achieved by the domain, and then we range all the way up to, well, we approach positive infinity. So we never include infinities. Because infinity is not a number, it's just an idea. All right, so E. So the domain there. So the domain would transfer down, that would be closed. This would transfer down, that would be open. But then this would come down and close that. All this stuff would transfer down, this would be open. Then all this stuff would transfer down and close it. Then all this stuff would be there. And then this would then be open at the end. So our domain would go from 1, including 1, all the way up to, but not including 4. The range would actually just be 1, 2, and 3. And just those 3 numbers, because all these numbers just kind of slide and hit just one exact number, we have a complete gap here and here. So we have a complete gap here and here. So I would just say braces, right? Just a regular set. 1, 2, 3. So just those numbers, nothing in between them. Okay. Be well.